All right, guys. Welcome back. Thanks for coming. I'm happy to see you back. I know it's a difficult hour. Oh. Thank you. What I was saying. Well, I just opened Moodle just to show you that I keep my uploads quite up. I mean, quite in line with my lecturing. If you checked recently, what happened here? Just this morning, I updated what the uploads for lecture 5. So if you go past lectures, see lecture 5 is right here. That's the content of Monday's lecture. All 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Well, first one actually wasn't part of the lecture, but I included this as a part of the lecture because one of the tutorial questions next week will be about that, and I included this so that I have a reference in the tutorial problem sheet right down here. So there will be a reference in the PDF file. You can click and you will come here to see the solution, unless you won't be able to recover the solution by yourself. So all of this, if you go through, many of them, yeah, with the comments. So yeah, eventually it's going to be a really lovely collection of materials when we finish with 24 lectures. I mean, if I will have enough stamina to keep up with this level of commitment. That's it. So let's just go back to the slides now. Hopefully it's not going to be too difficult today. It's mostly definitions and sort of example type discussions today, which is good for this late hour. Here we go. So I'd like to discuss with you what are the bounded subsets are, which is almost self-explanatory by the term itself. I have a separate file, which is put by Jonathan Kress about a few examples there. I'll show you them. So, yeah. That's how we normally define bounded subsets. That's the definition of it. Oh, yeah. So bounded subset, it's the one which you can submerge into a ball centered in the origin. It's said right here in the definition. A set omega in n-dimensional space is called bounded if there is a m number such that you see the distance from any point of your set to the origin doesn't exceed this m. So if this red spot here is your omega, any point within the omega from the origin, it's no longer than distance m. Or geometrically speaking, you just entirely submerge your red spot, your omega, into this green ball which sits in the origin. There are two examples of formal justification. There are two examples here of formal justification that something is bounded. So here, this first example, it says that any ball is a bounded set, not specifically centered at the origin. See, this is a ball with the point centered at the point x0. It is a bounded set. It sounds like an obvious statement from our a sort of domestic logic, but formally, if you want to see it through this definition, that's a few lines you have to put together, and these are the few lines. Look at this, what we say. We take x from this ball, which we want to convince everyone that it is bounded, and again, you see, the definition says there is. So when you prove that something is bounded, your job is to present this m, to make some substance under this there is claim. Here's a substance, here's a choice for the m, you see? We say, let's just choose the epsilon, which was the radius of the original ball, plus the distance from the center of this ball to the origin. If I make a choice of m like so, then everything works. And that's the argument which convinces everyone that it does work. Look at this. If I measure the distance from this x point, randomly chosen from this epsilon ball, to the origin, I can use triangle inequality. This is a step. That's a triangle inequality step. From x to x0, from x0 to 0. First piece is controlled by epsilon because it comes from this ball. Second piece, just we keep it as it is, but this together, this is a number m we chose. And that's the end of it. Yeah. Probably I should also mention that the m, the choice of m this slide presents, this choice is independent of this randomly chosen point x. That's important. Because this m, in a definition, it must be 1m for every point within the set omega you're testing to be bounded or not. You can't just alter your choice of m for different points. Yeah. Okay. Probably it's too much already for this relatively simple example. That's another example of Jonathan Kress. It's a set which is unbounded. Again, from our experience with this sort of sets, it seems like a quite natural thing that is unbounded, but here's a few lines which formally justify that. Let's just read through these lines. So the set itself is this set. It's a set of points such that xy less than 1. Geometrically, we know that's the area between two hyperbola branches. Here it is. So geometrically, we're having this sense that this is not bounded because you can stretch it infinitely into second quadrant and fourth quadrant. But that's how you formally can convince everyone that this is so. Look at this. Well, it's done by contradiction, actually. You see, it says suppose, it's the opposite, it's a contrary assumption. Suppose that omega is, you were able to submerge this omega into some ball of some radius m, centered at the origin. Imagine that happened. So it's a contrary argument. Look what it says. It says now, if you take this particular point, m plus 1, 0, and if you test for this point the condition of the omega set, it works because the product is 0, right? And that's less than 1, so this point also must be within the set. But this point is not within the ball, and that's a contradiction, you see? You just assume that the set is within some fixed ball, and then you produce a point within the set which falls outside that ball. That's the verification that the point falls outside that ball. That's the contradiction and the end of it. You have to realize you don't have to do this. You don't have to be this particular and detailed every time you say something bounded or unbounded. After some time, of course, we will just trust your judgment. But probably once we would need to test your ability to produce something like this. Yeah. So once, I suggest everyone try to for the questions which will be in the tutorial set in relation to bounded sets and unbounded sets. I strongly encourage you to produce something like this on your own, once, at least one. You don't have to do it every time, of course. If you do it every time you discuss bounded and unbounded sets, it will be, you won't be able to present actually the objective of your argument or whatever. But once, I encourage you to try to do something like this, to test your sort of naive understanding of bounded and unbounded via this formal approach. At least once, you have to do it. Any questions? And this is it. This is all we have on these slides. I'll go back to my main set of slides. In relation to the bounded sets, that's the result which we need to know. It's one of the fundamental properties of the n-dimensional spaces. It has a name to reduce help with the referencing. When you present something, you may just make a reference to this theorem. It's a very well-known result. Everybody knows Bolzano Weierstrass theorem. Look what it says. It says a set or a subset in n-dimensional space. It is, well, 3 claims in this theorem. There are 3 claims. All of them are equivalent to each other. The third one, I included this, and Jonathan Kress included this only for the purpose of just broadening your views and knowledge. It's a very high level of mathematics. You won't be dealing with the third clause, but the first 2, it is within your reach, within your level of knowledge of mathematics. And so it says this: the set is closed and bounded if and only if. Listen to this. Every sequence in omega has a subsequence which converges. Yeah. It's not true, of course, that every sequence within the set, within the bounded set, is converging. But the good point is, within every sequence, as long as it comes from the bounded and closed set, you can find a subsequence. It may be very sparse size subsequence, but still you can find that, which is converging. I'm planning to show you how this is often used in other proofs. The proof itself of this Bolzano Weierstrass theorem, we're not going to discuss that. Jonathan Kress put some notes, which is not a complete proof. Well, you can't really, of course you can prove this result. It's just, this result, it's one of the fundamental properties of numbers, and without looking into numbers from the very formal, very fundamental approach, you won't be able to really understand the proof of the theory. I mean, appreciate the proof of this result. That's why I'm not going to discuss that. But Jonathan Kress, in his notes, he put some comments in relation to that. I will publish these comments probably tomorrow. And if you want to read those, read those. On the other hand, I also, if you want to know more about this Bolzano Weierstrass, Wikipedia page also very good on this subject. But for our purposes, just knowing of a statement of the first two parts of this result, that's all I need. But because, yeah, that's all I plan to use in what follows. Now there's another piece of a definition, which is linked to the Bolzano Weierstrass. Like I said, today it will be mostly definitions and a few examples, which is a good choice for 5 o'clock lecture. It's called a compact subsets. Compact subsets, it's an easy definition. It says this, look at this. Omega is called compact if it satisfies either properties of the Bolzano Weierstrass theorem. So compact, you can say if it's closed and bounded, it is compact. It's the first part of the Bolzano Weierstrass. It's also compact if every sequence has a converging subsequence. It's also compact. Either way you can define it, either way you can use it. So compact, basically, it's the very short, very effective name for this property of Bolzano Weierstrass. Yeah. Here's the examples. I know not many of you, I mean, half of you have been through the tutorials already, the other half coming tomorrow through the tutorials. Oh, wait a sec, why do I say that? I'm not supposed to say that because you haven't discussed closed and open sets in the tutorials. No, never mind this tutorial remark. No, I'm just. I was meant to say that in your tutorials you're going to look for how to test for the open and closed subsets. We did a few tests 2 days ago, and now you're very well equipped to do those tests, but you haven't practiced on that. It will be next week. Yeah, but this slide, it sort of uses already now more or less what we know about closed and open subsets. For instance, empty set, it's a compact because you can test it either by the first part of the Bolzano Weierstrass, because it is closed and bounded, right? It is closed because its complement is open, its complement is a real line. That's right. You know why I stopped? Because I said its complement is a real line, but as a matter of fact, it depends within which scope you're talking about, right? If you think of an empty space as a part of the two-dimensional space, then the complement will be plain two-dimensional space. Real line is not compact, it's not closed. Or, for instance, you can argue like that. You see, I mean, you can argue by the second part of the Bolzano Weierstrass. The second part of the Bolzano Weierstrass says every sequence has a converging subsequence. And if you take real line, and if you take the sequence of all positive integers, it's a sequence. It doesn't converge, doesn't it? Why it doesn't converge? Well, because I mean, if you remember one of the necessary criteria for the convergence from the first year numerical sequences I'm talking right now, one of them says sequence converges. Oh no, wait a sec. It's for the series. How can you argue that the sequence of integers doesn't converge, positive integers? Why it doesn't converge? What's the simplest way to say it? I'm just wondering, how would you argue that? It doesn't converge, right? Or it does? Let's just clear this one first. So it does it or it doesn't? It doesn't converge. How would you convince me that it doesn't? Imagine I came from the outer space, never heard of that. Huh?
Do you have any maths in outer space?
Oh, forget the outer space. How would you say it? But why? Go ahead.
Would you, by contradiction, assume there's an n that it converges under, and then you're able to find a number that's larger than n?
Can you just repeat again? I didn't catch that.
So you assume that it does converge there exists an n which the whole series is under, and then you're able to find a number that's actually larger than n.
Right now you're arguing that the sequence is not bounded, rather than converging.
Oh, I see.
But on the other hand, it might be a way to do it, because one of the necessary criteria from the first year, they say sequence converging only if it is bounded. Unbounded sequence cannot possibly converge. Right? That was something in the first year. What about subsequence? If I take a subsequence of positive integers, does it converge? Can you use the same argument for that? Probably yes. Subsequence of the positive integers, it's also unbounded. Otherwise, it will be finite. And subsequence, it's always infinite. Yeah. Probably that's the best way to argue that. Yeah. That's why you see in R, I presented a sequence of positive integers which doesn't have a converging subsequence. Because if you take in the positive integers any subsequence, as long as it is infinite, and subsequence it assumes to be, every time you say subsequence, you assume it is infinite, it will not converge. Yeah. 0, 1 interval not compact because it's not closed. Remember, compact, it's either first part of the Bolzano Weierstrass or second part of Bolzano Weierstrass. 0, 1 with endpoints, compact because it's closed and bounded. Compact, S2, 2 sphere. Well, S2, it's a standard notation for the sphere, normal sphere as you know it in three-dimensional space. Remember, sphere, it's not something without the interior, just the surface of the ball. It's a compact because it's closed and bounded. Contour set. Do you know what the contour set is? You don't? Oh, never mind that then. Well, if you never heard of that, probably my description won't say you much. It's one of these freaky subsets which surprised mathematicians a lot. Those who were like concerned with problems in measure theory. I think it appeared somewhere in the beginning of 20th century, if I remember correctly. If you want to know more, you should read Wikipedia page. It possesses some very, very strange properties, but it's a strange properties for you probably, where you won't find it strange because you never heard of those properties. Well, one day, some of you who will continue your mathematical development, one day you will appreciate what's the counter set is and what's the benefits of that. Oh, it was an eye-opener at some stage of history. I mean, at some stage of the development of mathematics, it was an eye-opener discovery of such a set. Yeah, that's all I can say right now. It's a compact. I don't know. I mean, I just copied this from the journal. I can't argue that it's compact right now. Or maybe I can. Well, definition of the set, which is on the Wikipedia, it's sort of, from that definition, it's clear why it is compact. But if you haven't seen that definition, I mean, when you see that definition, you'll see it is compact. Because counter set is actually, it's a complement of an open set, and it is bounded one. That's why it is compact. As simple as this. Okay. Another piece of a definition which I have to mention. Again, it's another easy piece of a definition to expand our language. It's a path-connected sets. Yeah, let's just look into that. You won't be dealing with the counter set in this topic, so don't get scared. If you Okay. Here's a term, continuous path. Normal in this topic, we call continuous path is a term which is used to describe a function of this type. It's a function which takes 0, 1 interval into Rn. So it's a vector function, it's a curve to some extent, such that in the endpoints, the function takes the x and y values. Yeah, it takes x and y values. So it's a path connecting point x and y. Now a set. So look at this. We just extending our adjectives we can put next to the subset, right? We know closed, we know open, we know closure, we know bounded, we know compact. Now, probably one of the last ones, path.connected, adjective next to the subset. That's what we mean when we say path.connected. It says that if you have any 2 points within a subset, you can always connect them with a path, continuous one, which is entirely within a subset. That's a demonstration for you. If I take this annular region, that's the formula for that annular region. So it's a radius 1 and 2, inner radius 1, outer radius 2, dashed boundaries because they are not included, strict inequalities, but it's not really relevant for the consideration. 2 points, like these 2 red points which are on a graph, you can always connect them with the path, no matter where the points are. And Jonathan Kress went to this length. He even gave the analytical formula for this connection. Look at this. He said, if you have 2 points given parametrically, so here they are. If you have 2 points given by polar parameters, r1, theta 1, r2, theta 2, he gave the exact, explicit analytical expression for this path connecting these 2 points. Look at this, what he says. He says, for the first half of 0-1 interval, you alter the argument, theta. You see, r1 kept as with the point x, but theta runs linearly from theta 1 to theta 2. Yes. So that's this piece of a connection, this one, up to this point. For the second half of the parameter t, from 1/2 to 1, you alter the radius and you keep the theta 2 angle fixed. And the radius also altered linearly. Here it is, linear alteration. And that will be this little radial piece of a path. It is a it is a continuous path because it is continuous on the first half. It is continuous on the second half. And when you glue them together in this point 1/2, it glues together nicely. That's why it is continuous. On the other hand, at this moment, I have this urge to ask you, when I said this piece of it is a continuous one, how would you argue that formally? How would you say it's continuous? Why? How would you just, which theorem from what we discussed earlier you will reference in your answer? Yes, please. Elementary functions. Well, theta 1, it's elementary. Yeah, actually, I would agree with you. Yes, theta 1 is elementary function. Theta 1 is elementary function. Sine of elementary function, it's elementary function because it was the theorem we used. Cos of the elementary function, you multiply its elementary function. One thing troubles me a little bit. Polar coordinates. Are you going to just address that in your argument that the thing is continuous? How would you address that? Probably we should say because if you have 2 continuous functions, if you build a superposition of these 2, it is also a continuous function. It's a part of this algebraic properties of continuous functions. Yeah, then it will do. But mostly it's elementary function. Yeah, that's right. Thank you. Yeah. And that's why this is path connected. Any 2 points you can connect with the path, and here it is. Here's the example of not path connected set, and that's actually interesting because, again, Jonathan Kress went this length, and he made a quite careful formal argument why it is not path connected. So the set itself is this one. It's the set x, y bigger than 1. It's again 2 hyperbolas, and now the outside of hyperbolas, third quadrant. It's a diagram. Visually, I mean, again, after a while, your just experience, your naive logic will suggest immediately this is not a path-connected set. But formally showing that, look what he does. It's a good skill, actually, finding such a formal presentation. He says that, let's just take 2 points. He suggests these 2 points, 2 and 2 and negative 2, negative 2. Both of these 2 points, if you test this condition, they will give you positive, because 4 bigger than 1 on both points. Now he says, imagine it is path-connected set. Imagine again, contrary statement. It is path connected. So we might, if it is path connected, then we can come up with a continuous path which connects these 2 points. We can come up with a function phi from 0, 1 to R2 such that in the endpoints it delivers my negative to negative 2 at 1, 2, and 2, and it is continuous. And it is entirely within my omega. Here's a contradiction. Look what he says. Let's just take the first component of that function. It's a function which takes values in R2, so there's the first component, there's the second component. He gave name phi1 to the first component. That will be a numerical function from 0, 1 to R. And now listen what he says about this function. He says on one hand, this function in the endpoints of 0, 1 takes the values negative 2, 2. It's from here, right? It's from this assumption. That's why it does so. It's on one hand. On the other hand, we know this function is continuous. It's one of the theorems we had, right? Continuous function is so if and only if every component is continuous. We had such a theorem. And one of such theorems I even proved, I think. Oh, he uses beautiful result from the first year. He says, by the intermediate value theorem, such a function, numerical function, phi1, it is continuous. It's supposed to take every intermediate value between negative 2 and 2. And he chooses a very good one, 0 value, which my function is supposed to take. But if my phi1 function takes the 0 value, if you test at this moment in time, at this moment on your curve, you test this condition, it no longer works because 0 multiplied by anything else will be 0. And that's where the contradiction comes up. You see, the argument is very well tailored to this set. This usage of 0, it's very specific for this set. That's why coming with something like this for the other set, it will require skills from you. Try to do that. It's a nice exercise. I mean, the rest of it, the intermediate value theorem, this components are continuous and the function is continuous. All of this is it's a standard wrapping around your main idea, how to tailor this intermediate value theorem to particular look of a set. That's where the challenge will be mathematically. The rest is just a presentational challenge. I hope you understand what I mean. And basically, presentational challenge, you have this template, you just take it and use it. All you have to just substitute is this idea, which is connected to the set itself. Yeah, that's the end of it. Any questions? It's not my water. That's my water. All right, let's just go back to my main set of slides. Oh, it's a beautiful theorem. When I say it's beautiful, it's an easy one. I mean, the argument of this theorem is an easy one. Oh, look what it says. It says that if you have a continuous map between Rn and Rm, or between a subset in Rn and a subset into the Rm, then there are two things you can expect from such map all the time. Compact sets, they always will be mapped into a compact subset, and path connected into the path connected. That's all there is to it. It's a good theorem, and I hope it will be plenty of opportunity for you to reference this theorem. I will put this into my index. Remember, I showed the index 2 days ago for you to easy to find it in case you want to see the proof of it. There is a proof for this theorem, which very simple proof. It's a good one. It's not tedious one. It's really simple and beautiful. It shows you this both of the concepts of compact and path connected. It's really showed it nicely. And I have a proof, and I think we'll see. I mean, we will look at the proof. I will publish it anyway, one way or another. But before we do that, I think we can do the examples. So here's the theorem again. Let me just keep it a bit longer. Just look carefully at the theorem again, and then we can look into the examples. Right. So This type of questions, you will see a few of them in the tutorial set. When you have two subsets on the plane or maybe in 3 dimensions, and you have to answer the question whether it is possible in any way to come up with a map between S1 and S2, which is a continuous one, which takes S1 into S2, or some other combination. So here there are six different combinations, whether we can come up with a continuous function which take S1 to S2, whether we can come up with the continuous which take S2 to S1, the whole plane R2 into S2. All of these combinations, all of them are addressed. Yeah. We'll just look into that. Basically, there are just there are limited number of tricks or ways you can argue whether there is one or there is not. Most of the time, when there isn't such a map, there is no such a map, you will use this theorem on the previous slide. For instance, part 1 is exactly the case where you're going to use this theorem. Look what it says. It's the next slide. Yeah, it's the next slide. So part 1 is the same sets, it's just now they sort of printed in line. The part 1 says S1 is compact because it's closed and bounded, right? It's a unit disk, radius 1. It's bounded and it's closed because boundary is included. So it's a compact, whereas this one is not compact. And by the theorem 2 slides ago, we can immediately reject a possibility of a continuous map between these two. Because compact subsets must go into the compact subsets. There is no way under the continuous map. So here we just reject it straight away. Second one, well, the other way around, it says the answer is yes. Yes, we can come up with a map. And if you say so, you have to produce some map. And that's what suggested. Well, the map is given in terms of the polar coordinates. Again, it says this. The r theta point in, so we were looking at the map F2, which takes S2, this open disk of radius 1, into the closed disk, S1. So here's a suggestion for the map. Look what it does. It takes a polar point with the polar coordinates r theta, radius r, angle theta, into the polar double r theta in case radius less than 1/2, and the point on the boundary, radius 1, angle theta, if the radius bigger or equal than 1/2. Basically, the change happens, you see, in the radius component. Theta doesn't change. Theta all the time is the same. Only the radius is changing. Actually, I have a diagram which shows this. I have to switch to the dynamic slides to show you the diagram. If you don't mind, I will. How do I do it? I didn't open it, right? Here it is. So it's your open disk, that's your closed disk. Well, this one we say we know the answer is no. It's again, I'm just repeating the first part because this is compact, this is not compact. Well, for the second part, we do have a map. That's a definition. I just repeat the same definition from which was on the other slide. Here it is. It's the same definition, but here's a diagram. So this is this is what happens with R. This is what happens with R. This is 1/2 point. This is a point 1. So R is double R when R is less than 1/2. So on this piece of the X, or on the horizontal axis, that's how the function look. On this, or beyond 1/2, it's just 1. So what happens with this disk is this. You take this inner disk of radius 1/2, and everything within this disk, except the boundary, you double, you just stretch it radially, and that will cover everything. That will make you this disk without the boundary, but then everything outside this 1/2 disk within this, why don't I picture this 1/2 disk? Can I do that? I think I can. I just hope it will work. No, it doesn't. How come it doesn't work? I know why it doesn't work, because it's supposed to be U here. Yeah, here it is. I can take this 1/2 disk, everything within this disk, except the boundary. Everything within this disk, except the boundary, it stretched, it doubled in size, and that will cover everything within here, except the boundary. But everything outside, it just goes straight into the boundary here. You see, 1, radius is 1. It's quite artificial map, but it does the job. It takes this disk without the boundary into this disk with the boundary, and that's why you have the answer to the question 2. Right. Question 3, I think on this, I have it on this slide as well. It's a question whether you can take the whole plane into S2, whether you can sort of squeeze the whole plane into this disk without a boundary. Again, the answer is yes. It's a rather standard construction. It's again a construction which is given in terms of the polar coordinates. Yeah, so basically you don't change your angle, but you use the inverse. You use the arctangent function in order to squeeze the half line 0 plus infinity into the 0, 1 interval without 1. Use the arctan to do that. That's the graph of the arctan function. Half of the arctan function. So you see what the function does. It takes the half line and maps it into 0, 1 interval. It's a 1 point, and the 1 point is not touched, and that's fine because we need to map the plane into the open disk. You see, S2, it's the open disk. It's the 2 typical constructions which you can do, and if you disprove something, the typical argument will be via compactness or path connectedness. It's the theorem 2 slides ago. Yeah, that's all I have on this dynamic slide. Now I want to go back to my main set of slides because there are a few other questions there, but they are already derivative of the previous of the main one on the first ones. Yeah. So 3 we just done. I just copied the same thing on dynamic slide just to show you the diagram. 4. What was 4? Oh, I forgot what was 4. I need to go to my slide before to see what the 4 was. That's why I don't like this sort of. Okay. 4 is the one which take the plane into S1, into the closed disk. Okay. I don't know. You may probably with some effort you may come up with a direct formula, but the answer here suggests we can combine F2 map and F3 map together, and that will do the job because F3 map does the open disk, F2 maps the open disk into the closed one, and that's the fifth one. It's the one where you have to do the opposite map. You just take the inverse of F3. Oh, 6. What was 6? Let's just check what the 6 was because it's interesting. 6 was whether we can take S1 to R2. Well, we see we use the compactness argument because this is a compact subset and the whole plane is not compact, so we know we cannot possibly take closed disk into the plane. Open disk S2 we can, and that's the inverse of a free map. But the closed disk we can't because compactness again stands in the way. It's part of the theorem on the previous slide. That's the examples. Any questions? Oh, now I think we have a time to the proof. For the proof, 10 minutes is exactly the good time to see this proof. It's a short proof and it's an easy proof, but it's a beautiful, it's a good proof. In terms of, it shows you some good tricks and the good things you can do with the path connected and compact sets. It's a proof which is put together by Jonathan Kress. I will use this PowerPoint presentation for that. So before we go there, I'll roll back to the statement of the theorem. Look at the theorem again. Here it is. So again, we have a continuous map, and I have to convince you that such a map will always take compact subsets into compact subsets, and will always take path-connected subsets into path-connected subsets. I do have a proof. What was the name of it? Let's just check. Yeah, it's this file. It's an easy proof. Easy, I mean, it's like a forward motion all the time, no tricks and anything. That's the theorem. Look what the first part says. We start with the assumption f is continuous, k is compact, and we're going to use this second part of the Bolzano Weierstrass theorem. Okay? For the proof of this theorem, we're going to use the second part. So the part which says a set is compact if and only if every sequence has a converging subsequence. If it's so, we call it a compact. So we're going to use this part for the proof. So you see, it's actually very typical. When you test a subset for being compact, you use the first part of the Bolzano Weierstrass. You test that it's closed, you test it is bounded. But when you prove something, some statement about compacts, second part of Bolzano Weierstrass is your choice most of the time, like in here. So look at this. I have to convince you that if I take any sequence in the image, fk, it will have a converging subsequence. Right? So here's my sequence, yk. It's a sequence in the image. Look what I say. Because it's a sequence in the image, it must have some points which produce that sequence. It must have some points in k itself, which make yk as the image of xk's. Otherwise, they won't be in the image. Now, this sequence, this new one, xk, it is in k, which is assumed to be compact. And so for this xk, we do have a subsequence, because k is assumed to be compact. K compact, so there's a convergent subsequence xk. Well, that's, I think, letter L, little l. That's how you normally write a subsequence. You take a k and you index it with something, kl, and this subsequence will have a limit. And that has a direct implications for the y sequence, because now I say if I take images of this subsequence only, and I give name to them, ykl, y sub k sub l, this will be a converging subsequence because xk was converging and f is continuous. Remember, there was one of the theorem we had. Converging sequences taken to converging sequences by continuous map. So f of this xkl will be also converging, which is ykl, and this is it. For the sequence y, we found a subsequence, ykl, which is converging. And that's the end of the proof. Of part 1. Part 2 is almost identical, almost equally simple, almost equally straightforward. Look at this, what it says. No, I'll take it back. Don't worry, you can stop me. We have time. That's why I don't like PowerPoint as well. It's just too quick. And just it encourages you to, not you, me, it's flip too quickly through it, right? But either way, you know, this will be published on the website. Not today, tomorrow, most likely. So even if you didn't take anything, you can take that off the website. All right, time to go for the second one. So this time we assume f is continuous and b is path connected. And I have to convince you that the image of b will also be path connected. So I take 2 points in the image of b, y1 and y2. I need to produce a path connecting these 2 points. And I'll do it through b itself. Look at this. Because these points come from the image, they must have some pre-image points, x1 and x2, in b itself. Like this. B is path connected. So these 2 points, we can connect them because b is path connected. So for these 2 points, so there's a path, there's a map, phi, 0, 1, b, which take x1 and x2 as the endpoints, and which is continuous. That's an important remark. Now what do? How do I come up with a path which connects y1 and y2? Quite expectedly, I just take composition. of f and phi. Composition will take 0, 1 into the image f of b, and that will do the job. It will be continuous as a composition of continuous functions, and it will do the job. At the end point, it will take the point y1 and y2. That's the simple arithmetic which convinces everyone that this is so. And it is continuous because it's a composition of continuous functions. And at the end of the proof. So it's a very good proof in terms of, again, it doesn't represent much of the challenge mathematically, but it's not as tedious as, for instance, algebraic properties of limits, continuous functions, and everything like those also do not represent any challenges, but those are tedious ones. Whereas this one is light and easy, refreshing, I'd say. Any questions? Well, if you don't have any questions, I think we can wind up for today. Thank you very much. I'll see you all tomorrow.